enough with crazy topics. Let's go back to the good old BSM, right? Yeah, I mean, Giovanni will tell us about the MSSM, right? Beyond the TeV scale, a bit less natural MSSM. And then we move to flavor with Lorenzo in the second talk. Please.
Thank you very much for having me here. So I will start with a disclaimer. I'm not going to give a fair overview of the status of SUSY in 2025. Rather, I will give a very biased view of what I understood from about SUSY from the LAC data so far. And maybe I'm going to convey why I still believe that looking for supersymmetry in the next generation of collider makes sense. In fact, I want to convey why I believe that among all the possible scenarios of beyond the standard model physics that can be probed in the next, let's say, generation of colliders in high energy, supersymmetry is still the most plausible to me. All right, so let's start. So supersymmetry is, of course, the symmetry that relates bosons and fermions. And it is, at the theoretical level, is basically the largest extension of the Poincaré group that is compatible with the fundamental laws of quantum mechanics and Poincaré invariance. And for this reason, looking for supersymmetry and discovering supersymmetry is not like looking for most of the beyond the standard model physics that you look for. You're really looking for some fundamental properties of nature. In fact, for example, the only perturbative calculable implementation of quantum gravity that so far we know, it's hardwired connected with supersymmetry. So, of course, we don't see supersymmetry as a symmetry in nature, which means that our vacuum, while it's approximately Poincaré invariant, well, yes, requires that it's not invariant under supersymmetry. And so the main question is, at what scale we expect supersymmetry, at what scale supersymmetry is broken if it's there as a fundamental symmetry of nature. So historically, the main motivation to expect supersymmetry to actually appear within reachable energies was, well, these three, at least these three are the historical motivation that was fed when I first learned about supersymmetry. And in order of how much strong they were in requiring supersymmetry to be at around the weak scale, the hierarchy problems, dark matter, the Wingpin miracle, and the grand unification. So let me now briefly go through those arguments to see which one we can throw away, not having seen supersymmetry yet, and which one we might want to retain. So I start with the hierarchy problem. So of course, you know very well, the hierarchy problem is basically the problem associated to the fact that in the standard model, weak scale is quadratically sensitive to new physics. In supersymmetry, this corresponds to basically to the fact that you receive corrections to the weak scale proportional to the scale of restoration of supersymmetry squared. And this was one of the main arguments to expect why supersymmetry at the weak scale, right? Now, this is what happens after LHC. So we haven't seen any supersymmetric pattern of the standard model. And in some cases, present searches push the superpartner to be to a multi-TeV scale. So this means that we might expect within supersymmetry corrections to the weak scale to be around a couple of orders of magnitudes larger than the electroweak scale, which means that at the supersymmetry restoration scale, let's say it's around TeV or above, you need a cancellation of order % or better to explain the hierarchy that's between the electroweak scale and the scale of the superpartners. This is very roughly, right? So at this point, you might okay, this is a very naive estimate. Maybe you just need to be a little bit more clever. And in fact, this is what was part of the exercise in the 2010s to build models which basically could improve this level of cancellations in a natural way. And then we understood that basically you can trade in some extent the amount of tuning you have to do with the number of complexity of the model you have to introduce. However, none of these models were found either. This is in the concept of supersymmetry. And in fact, if you look at a little bit more in details what these models were doing, they were introducing more complexity, which means extra assumptions. And then you can start worrying that if you put like of order 10 natural assumptions, to do the 10 is of order 1,000. So if you factor in also all the assumptions in, this curve probably is more flattened than it looked like, right? So probably this way you are not really improving on the plausibility of this scenario with respect to the minimum ones. Of course, you can say, okay, but this is just about SUSY. Maybe this is not the solution to the hierarchy problem. In fact, people explore many other alternatives. In fact, there are many other alternatives to the solution of the hierarchy problem besides supersymmetry. None of those has been found yet. Some do better at the level of tuning, but they often have other problems. For example, flavor problem, EDMs, and so on and so forth. So at the end of the day, they don't look more plausible, at least in my view, than the supersymmetry itself. But maybe the bigger elephant in the room, this is the elephant in my room, is the fact that the similar arguments, if you extend to the other bigger hierarchy problem present in the standard model, which is the CC, fail in a much worse way. So in fact, supersymmetry is also able to cut off the cortical divergences in the cosmological constant. But if you apply the same scheme, you'll find that it already failed by many order of magnitude. And maybe to make the things even stronger is the fact that as long as we know, supersymmetry is the only symmetry that actually would cut off this divergence for the CC. We don't have any alternative to supersymmetry to make the CC small in a natural way. So within supersymmetry, then if you worry about the hierarchy problem, the delay of discovering of supersymmetry should much more worry about how much it worsens the CC problem than the weak scale. In other sense, you get a much stronger pressure to have low energy supersymmetry from the CC than from the electroweak scale itself. So, well, because of everything, of course, also running, everything breaks scaling bands. Yeah, also, I mean, I need to see a non-supersymmetric scaling band model which is natural. No, but then it will be technically natural. It's just a question of why the scale is small or large. It's like a mu term, right? You can put it small, it will stay small. It could be at m Planck, it could stay at Planck. Sure, supersymmetric. Yeah, then it could be minus m Planck to the 4 or near to 0. It's a free parameter. It's technically not, every value will be technically natural. All right, so here it seems that we are missing something, of course, and something big. Of course, there is always the spectrum of some anthropic reasoning, why the scales has to be the way they are. These are very difficult arguments to make because we don't know the landscape, we don't know anything about how the vacuum are selected and so on. So, but of course, you have to always take into account this possibility. So if you cannot find any dynamical reason or any new degrees of freedom that will explain this hierarchy, of course, you can always in principle suspect that the real reason is such. So the second argument was about dark matter. So in a natural SUSY scenario, typically the lightest supersymmetric particle, which is stable, could be a neutralino, and it will have the right parameters to explain the right abundance of dark matter. Now, not having found a completely natural SUSY and not having found from the red detection neutralinos or any WIMP that will have sensible cross sections with the nuclei, basically does not rule out the possibility that the WIMP could still be dark matter in SUSY, but in a sense, for me, it would be kind of a miracle if they were. In the sense that now it's really get some non-trivial constraints in your spectrum in order for the spectrum of supersymmetry to actually reproduce the dark matter abundance that we observe. So for example, you get a very sharp prediction, for example, for the Buino or the Xeno in case you want to reproduce such abundance. Besides, by now we will know many other alternative scenarios which are equally plausible to explain matter, as plausible as the original WIMP miracle, like misalignments, dark sector, gravitationally produced particle from the early universe. So in a sense, this argument here is not as strong as it was viewed before to prefer supersymmetry versus any other beyond the standard model physics at the TeV scale. Finally, grand unification, was already mentioned by before. So grand unification typically is basically comparing the unificational coupling between the standard model and the MSSM. This is one picture. So different people have different reaction when put in front of these plots. Some will say, of course, look, MSSM, how good it works for the unificational coupling. It's clear that it's there. On the other hand, some other people will say, look, the standard model almost unify within maybe 10, 20%. So maybe there are some threshold at that scale. It's still good. I don't see a big preference towards MSSM. So let me just sketch the way I see. I like to think about this. So let me take grand unification seriously. Let's take two of the gauge couplings. Let's say hypercharge and weak coupling. Run them at when they unify, and then use this value to predict the third coupling at low energy, and do this exercise in the standard model and in supersymmetry, in low energy supersymmetry. These are the prediction for the standard model. So see here I put some error bars. The error bars are just the difference between the running if you do a one loop and two loops. So this is if you want to measure the typical effect of threshold corrections that you might expect at a high energy scale. You see there are different prediction both for the unification scale and for alpha strong. You compare with experiments. And the experiment like here, there is a bound from proton decay, but more importantly, the value of alpha S, it's very nicely agreement with the prediction from SUSY, while it's many threshold effects away in the standard model. So it means that the standard model could be made compatible with the grand unification if you are willing to incorporate some large threshold correction at the gas scale of order like 10 times what are the difference between the two loop and the one loop effects. So it means that, for example, if you put a lot of multiplets in the gut scale separated by order 1 in mass, you might land here. But then, for me, the weird feature of this scenario will be why I will start adding a lot of correction, a random walk left and right. I will end up at the same point, which is predicted by having a symmetry, which is a supersymmetry. So it seems a little bit fortuitous. Yes.
MSSM running. So you
Yes.
to happen.
Any? 5.
5s, 10s, 16s.
Right.
You don't decide if there is a gap.
For alpha S is unimportant, right?
Not important.
No.
I mean,
because a complete representation of SU5. Yes.
Okay, it's not moving.
Yeah, if you
alpha
go
itself.
strong, yeah, if you go towards strongification, yes, you will
Okay.
increase the error bars there. Yeah. All right, so so it seems for me some evidence that supersymmetry is there. Unfortunately, of course, the running is only logarithmically, so it's not alone, it's not a strong enough argument to expect physics at the TeV scale. In fact, if you start raising the scale of supersymmetry, in particular within a split SUSY, you raise the masses of the Fermi, which are mostly responsible for unification. You see that before you start deviating from the prediction, you have to raise the scale above 10, maybe 100 or 1000 TeV, which means that you prefer low energy SUSY, but this low energy could easily lie above the TeV scale. So it's only logarithmically there. All right, so now I want to first suggest a new angle. I will not use the hierarchy problem, which you don't understand. I don't want to use dark matter. I take seriously Lagrange unification, so I want to maintain the success of supersymmetry. Assume that supersymmetry is some symmetry, fundamental symmetry of nature at even some arbitrary scale. And then I try to just use experiments to determine the scale of supersymmetry. Okay, now here there are two scenarios. So if you think about the standard model in terms of energy, you get two scenarios, depending if supersymmetry restoration will appear before or after new degrees of freedom that appear in beyond the standard model. We know that there will be probably new degrees of freedom to explain neutrino masses or inflation, baryogenesis. We don't know if supersymmetry will appear before or after. So if supersymmetry appear after, some new degrees of freedom appear before the restoration of supersymmetry, there is not much I can say by just using experiments to determine the scale of supersymmetry. If on the other hand, the supersymmetry appears before any other degrees of freedom, then there is a regime in which the effective theory is the MSSM. And now, as you will see, I can say something non-trivial just from the experiment on the scale of supersymmetry. So for the rest of the talk, I will assume we are in the second scenario. So the point is that before supersymmetry breaking, right, the MSSM has one parameter less than the standard model. The quartic of the Higgs is basically predicted in terms of the standard model parameters. And which means that there is at the supersymmetric level, there is a relation between the Higgs mass and the Z mass, which is parameterized by this angle tangent beta, which is basically measure the ratio of the waves of the Higgs doublets. So it's basically predict that the Higgs mass must be below the Z mass. Very good prediction. At the quantum level, there are corrections to this formula. And here is where you start being sensitive to supersymmetry breaking. In particular, there is the largest correction comes from the top and stops loops. There is a logarithmic dependence on the scale of SUSY breaking, plus some other correction, which is instead bounded to be of order a few at most. So in principle, here you could invert this relation and try to predict the scale of supersymmetry breaking in terms of standard model parameters and some of the other parameters of the MSSM. So if you plug numbers in to reproduce a 125 GeV Higgs, maximizing this contribution that will be so if you assume tangent beta is moderately large, you need quantum correction to be as important as at 3 level of order 90 GeV square. Of course, this is not the breaking of perturbation theory because, of course, these corrections are in terms of some other coupling, not the same that appear at the 3 level. All right, so now if you want to, of course, invert this relation, since the Higgs mass depends logarithmically on SUSY scale, it means SUSY scale depends exponentially on the standard model parameter, so you need a high precision. So this is what basically triggered a lot of calculation at higher orders for these things, of which some of the bigger contributors are also in the audience. And this is what you will get. So as a function of the scale of in this plot, in terms of the scalars and the fermion partners of the standard model, this is, so here is a logarithmic scale, so this is in TeV, 1, 10, 100,000 TeV. You have to land inside this region here, depending on different values of tangent beta. And here I'm assuming that there are no large stop mixing, otherwise you can go a little bit below here. Now, if you take seriously grand unification, you cannot afford the fermions to be too heavy. So you want to be, let's say these are areas where you basically predict the right unification within 1 or 2 sigma in threshold correction. Okay? So in particular, basically this is what it's telling you is that you don't want fermions to be heavy. In this case, this means that also the scalar cannot be much above 10 to the 5 TeV in order to reproduce the right Higgs mass. And actually can only leave such large values of the scalar mass if you can have a small tangent beta close to 1. Now, despite the fact that, okay, in this case, of course, a small tangent beta, this means that the Letruy scale will be more tuned. The question is, can you actually tune? How simple is to tune the Letruy scale to be small? The fact that you can tune it doesn't mean that it's automatically so easy to tune. So tuning the Letruy scale just means that one of the eigenvalues of the squark mass, of the Higgs mass matrix is small, which means the determinant is suppressed, is close to 0. Now, if you request grand unification, basically means that the mu term must be small, the xeno must be light. So they will not participate in this cancellation. And this means that in order to achieve Letruy symmetry breaking a small tangent beta, you need to basically have this determinant to be close to 0, which means you have to tune B mu term against MH up and MH down, the soft terms of the Higgs. Now, in this limit, tangent beta is going to be just the ratio of MH down over MH up. So having small tangent beta means that should achieve the 2 soft terms of up and down to be close. But there is no actual symmetry that protects these 2 soft terms to be close. In fact, you cover running already retune them. So even if you start with boundary conditions at a high scale for which MH up and MH down are close, MH up is driven to be much smaller than MH down, driving basically tangent beta larger. So I don't want to say that it's impossible to leave here a small tangent beta, but this requires some extra work. It seems that the theory doesn't want to do that. No, I'm not using. What do you mean I'm using? All right, I don't want to tune everything. I just allow for the Higgs to be tuned. The Higgs to be tuned. So I don't care if the determinant. I allow this tuning, but then beside this tuning, I also now have to. If I want tangent beta to be 1, I also have an extra tuning, right? Because I want at the same time tangent beta to be 1 and the Higgs wave to be small. So in other words, I can have a small electroweak scale, but typically tangent beta will not be very close to 1. All right, so now if you concentrate to large tangent beta, then the Higgs mass will basically tell you something like this. So depending on the stop mixing terms, the soft terms, in particular the stop mass, should be either around 10 TeV, or it could be as low as 3.2 TeV if you happen to have large mixing parameter for the stop. So if we knew the Higgs mass before the LSC, maybe we would have done this exercise before, and we will not be so confident that supersymmetry will be around the corner at LSC. Maybe we would even have skipped the LSC and aimed directly like SSC-like experiment to probe higher scales. So here I like to quote Thomas Hobbes, hell is truth, seen too late. So let's recap. So the MSSM, in principle, have less parameters than the standard model at the supersymmetric limit. After you add Susy breaking, however, you end up with a plethora of parameters. Most of them just create problems, and in particular, make the theory much less predictive and introduce extra problem with flavor, EDMs, and so on. So the way these parameters are determined depend on the mediation mechanism, with how you propagate supersymmetry breaking to the visible sector. And there are many different scenarios: gravity mediation, normal mediation, gauge mediation, and so on. So you basically have almost one of model for each choice of the parameters that you want to recreate. Now, among all of them, I think now, for me, one emerge as more plausible after all we have seen so far from experiment. And this is the one I will concentrate most of my attention on for the rest of the talk, which is the so-called minimal gauge mediation case. As we will see, it's the most simple, most predictive, and most compatible with experiments scenario. So the idea is very simple. So you have the MSSM, supersymmetry is broken at some scale root f, and you just need to introduce some mediators, some extra field which is charged on the standard model gauge group, living at some mass scale m, and interacting with the Susy breaking sector. So this will generate soft terms controlled by a scale which is f over m, proportional to the root f, and inversely proportional to the scale of the messenger, m. And there is some extra freedom here parameterized by this n, which corresponds to some effective number of messenger. But this parameter n can only vary within a few if you want not to run into problem with Landau poles and so on. As we will see, it will not play a big role in the prediction of the model. So then, okay, so this is just the assumption of the model. You can compute the full spectrum of particles. You will find that basically gaugino and scalars are all proportional to the scale lambda times some calculable coefficient, which it only depends on the gauge charges of these particles. And this has very nice implications. For example, the masses of the squarks are proportional to the identity in flavor space, which means that they are flavor blind. They basically realize minimal flavor violation scenario, which means that there are no dangerous flavor change in neutral current. All flavor constraints can easily be satisfied. The A term and the B mu term actually are 0 at least a leading order at that scale, which means that there are no CP violating extra phases in the model. So there will be no constraint from electric dipole moments after having fixed the theta term, of course, in the standard model itself. So the only parameter here you see is this lambda and this n or root n. So some combination controls the masses, and then basically lambda times root n, and then some root n is just the ratio between, control the splitting between scalar and Fermi. So we started with one parameter less in the supersymmetric limit. We added one parameter. So at the end of the day, we will have the same parameters of the standard model, which means that we can predict the whole model, the whole spectrum. There is only a weak dependence on this square root of n, as we will see, and a weak dependence on the amount of running that you have to do from the scale where you generate the soft terms at m all the way down to the MSSM. As we will see, these two uncertainties are not the large uncertainty of the spectrum that we have today. So to see how, so why this model was not discussed as much in the past, was rapidly forgotten because of what is called the mu problem. Of course, if you want to address the hierarchy problem, right, in this scenario, you need that both the soft terms and the mu term, which is supersymmetric, lie at the weak scale. And there is no real reason why these two scales that do not speak to each other, they will end up at the same scale. And models that try to address this problem will produce what is called the mu b mu problem, which will predict some relation between b mu and mu, which was very bad for the generating a natural electroweak scale. And then those models that would then add and fix the mu b mu problem will reintroduce often all the problems that minimal gauge mediation was avoiding, like EDMs and predictivity. All right, so let's see then why we can neglect this mu problem. Well, so we have two scales, right? The scale of soft terms, M0, and the mu term. If the mu term is larger than this scale, there is no electroweak symmetry breaking because all the masses are dominated, or the Higgs are dominated by a positive contribution from mu. If the mu term is smaller, the Z mass, the electroweak scale will be at the scale of the soft terms, and this now is excluded from experiment. So the only way to generate a hierarchy between the weak scale and the soft terms is by tuning mu against M0. So if you want, the tuning that we have to do to generate a light electroweak scale is the same as the mu problem. They're one and the same thing. So basically, the relation between these two scales is fixed by fixing the right Z mass. The overall scale instead will be fixed by the Higgs mass. So we don't have any free parameter. So at this point, B mu and A will start from 0. The scale M will run down. They only generated radiatively. So the A terms will be small. So there will be no mixing, negligible mixing parameter. B mu terms also will be suppressed. This will automatically predict the large tangent beta. And there will be no CP violating phase because all the phases will be aligned. So you plug all the numbers in, and this is what you will find for the full spectrum of supersymmetry. You see that the color particle lies between 10 and 20 TeV, while electroweakinos and sleptons, they range between a few TeV to 10 TeV. So these are the gauginos, the Higgsino, the squarks, the slab, so on. So for each particle, you see four predictions. The difference between these bars are basically the effect of changing the overall scale of running and the number of messengers. So you see that the difference are not that big by changing these parameters. Most of the uncertainties in this prediction actually come from the experimental value of the top mass. So if you remember, the way we fix the spectrum is through inverting the relation with the X mass. So it's exponentially sensitive to the top mass. So the largest uncertainty in the spectrum of this scenario is basically set to our knowledge of the top mass. The next error will be due to the threshold correction at the standard model scale. So the standard model calculation, not even a supersymmetric case. Yes, not yet as important as the top. Yes and no, because you have to run them at a high scale. But well, you put the numbers in, you see that, yeah. You really need to go above 70. Then it starts dominating over the top. Huh? B mu ranges here, the tangent beta, if you want, which is the ratio between B mu and the MH up, MH down, and mu term. It's range between 30 and 60, depending of where you are in these bars. Okay. Okay, so these blue areas are the expectation. This is from 2015. The expectation for the reach of LHC8 that was available at the time, LHC14, and another TeV collider. So, for example, Gluino searches back then they were around 1.5 TeV. Nowadays, I think they're around 2.5 TeV. In fact, it's more or less here. But you see that are still far from reaching the model. This for Buinos, searches engage mediation, 600 GeV for this, and probably they will arrive up to here. This is staus. So if you have large, let's say, if for some choice of the number of messengers, the stau will be the NLSP, and actually will be collider stable. So you can look for it. With the old data, the bounds were around 500 GeV. Actually, this is a promising channel to actually produce epsilon-scalar X, because a large tangent beta, you can produce it via glue fusion with the bottom, and then indicates to tau-tau. So a large tangent beta, back then, the bounds were already 800 GeV. The latest bound, for example, from Atlas, almost reached 2 TeV, depending on tangent beta. So they start to be the lower part of the allowed parameter space. So possibly this could be the first particle that you will discover in this case, this scenario. Okay, to summarize, minimal gain generation. So you see that this model is, as of now, is fully calculable. It's fully compatible with the non-observation of flavor violation, no observation of EDM, no observation of proton decay, no observation of WIMP dark matter. In this case, in fact, the LSP will be the gravitino. And no observation of SUSY at LHC, unfortunately. But all SUSY could be possibly within reach in the future under TeV scale collider. So as of now, this seems to me one of the best motivations to expect new physics within supersymmetry at the 10 TeV scale. In fact, I think it could be a good benchmark even to design future colliders. In the other words, probably you may want your parameter to be such that you don't miss such a scenario. So we are at the moment looking at what are the minimum requirements for a future collider to be sensitive to this scenario. And more in general, independently of the scenario, TeV SUSY is, I think, is still a well-motivated and plausible scenario for BSM. If you think that tangent beta, given the boundary condition we gave, TeV large tangent beta is still probably most plausible within the MSSM to be compatible with grand unification. And at the end of the day, you're still left with 10 to the minus 3 tuning, 10 to the minus 4 tuning. It's not as bad as in the standard model. And that's all I wanted to say.
Thanks, Giovanni.
Case of the spin to Gravitino, additional bounds from BBN, Gravitino problems, all this story applies to this parameter space?
Yes, it applies. This is what part of the things that we're now looking at. There is a window of Gravitino masses that is still allowed. It's not overproduced. If you want, here is probably the most ugly part of all this scenario, is that you cannot afford a rating temperature which is much above the 10 TeV, 50 TeV scale, because otherwise it will overproduce the Gravitino problem. But okay, now it's a cosmology question. I don't know how much strong such a constraint is. Of course, you have to do baryogenesis below that. And, yes. Yeah, there is some part of so the Gravitino that is allowed is between 0.1 and 10 30 GeV. So and towards that boundary you start having BBN bounds.
So the first thing you want to know is the top mass now, and some refined measurement or prediction of some other parameters.
If we have a better determination for the top mass, in principle, that scenario could be determined with much higher accuracy.
And then you can determine the energy of the collider that you need after.
Yes.
So again, let me call it the wine bottle plot, even though the stop XT plot.
The stop?
I didn't know it was the official name, octopus plot. I mean, okay, first to say that not this very same version, but there is a risk that in the briefing book, this will be the first plot of the chapter on BSM. So we anticipated your suggestion to take this as a serious benchmark for future projects. It's not going to be covered entirely, not even by FCCHH.
It's not?
It's not. The read in stops is not enough, unless I misremember. But the very top of the, yeah.
Very top, I mean 15.
More than 12 or so TeV is probably outside.
But even if you do associated with Gluino?
No.
Because these are, if you use minimal models, then I can believe it. But now, if you're really looking for this scenario, you could improve by looking at.
No, my actual question has to be the large step tangent beta here.
Yes.
At top matters, tangent beta for strong matters. If one is maybe, I think somebody PPG is copying the relation from dragging it, I don't know. So how big actually the bigger room to maybe gain 20-50%, which in terms of decades of running
These error bars, you mean?
Yes.
No, but these error bars, you see this dashed line is due to the top mass.
Only the top ones.
The dashed.
Tangent beta, if you maybe are a bit more liberal with your requirements on GATS or...
No, tangent beta, depends tangent beta is very small because once you are a large tangent beta, the correction goes like 1 over tangent beta.
Fine, but if I go back to motivation where you tried to say correctly that GAT
Sure.
plus...
Yeah, here.
Yeah,
So
exactly.
instead of taking order 50, take 4.
4, or maybe you allow you...
Sure. Sure. Not in that detail, of course. Of course. You could put a bound on tangent, how small tangent beta you could be sensitive to, but right, at that level. I mean, within this framework, I can be more specific because it's predictive, right? This one. Now, if you start moving each part around independently, no, I don't know. It's the usual, can always, after having run under TeV Collide and not seeing Supersymmetry, you can always deform the model in such a way that, like it has been done for.
So the Gluino and...
There is no guarantee. Huh? In the worst case, in which you take basically the top mass at the lowest. Now here, I don't remember if this bar are 1 sigma or 2 sigma top mass. We are going to re-update this with, in fact, this is a little bit optimistic in the sense that this is the top mass of 2015, which was 173 something. Now it went down, which means that the lowest part of this bar, the lowest part of this bar are lost. Well, the tangent beta here is not fixed. It's the one predicted in the model. So in different parts of these bars will be a different value of tangent beta, depending on the running of everything. So tangent beta is not a free parameter in this problem. It's predicted by the theory. It's predicted. Because I have the same number of parameters of the standard one. So B mu starts from 0, runs, and whatever it ends up at the weak scale.
It's a combination of MA, you have MA, mu, right? It's some...
Yes. Yeah, you can rewrite, yeah, you can determine in terms of, but it's also image up, image down that I didn't write here, so.
If I also forget about unification, is it still the only way to go to large masses to go to small tam beta, or if you fill in the like lower diagonal part of your other plot, you can do it also at big tam beta?
Right, here you could leave here without unification, you could leave here. This is like what is called high scale SUSY, right? It's not even split.
Yeah, but if you go below, does anything change, or
I think
you still
could
need
go a little bit? You could still go. I didn't plot it. You could still go a little bit below. There, at a certain point, of course, the M0 are attracted by M1 right? So you cannot make M0 much lower than M0.
Sure. Okay. So the saying is that you still need small tam beta to go to very large scales and not see anything.
No, there is a caveat.
Okay.
You can go to scale even larger than this, much larger than this, if you go to very large tangent beta. Because then you start to be dominated by the bottom. And then you can show that there is a window where you're still perturbative, and you can go to even higher scale. So, but okay, this is really tuned.
No, yeah, it was just to have
we have a plot about that in the paper.
Thanks.
So these things we know since 2012.
Yes.
Indeed, your paper is from 2015, and this is.
Yes.
So what have we done in the last 10 years? Dark photons. No,
yeah,
really. I mean,
the problem is sociological.
Exactly, but what is our problem?
No, the problem is that in 10 years we don't have a new collider. If in 10 years there is a new collider, I think most people will work on collider physics.
No, but I think even in the community that works on future colliders, this message is not completely clear, I think. There are people that say LHC failed in delivering SUSY. There are people that...
Now, of course, there is a change in paradigm, right? The reasoning around this are completely different from the reasoning that were run before LHC. It's not about a hierarchy problem. There are some assumptions, so it's not a guaranteed, not at all. But it's still plausible, huh? The mass? It is very important, but there is still the assumption that there are no new degrees of freedom before SUSY. Then you can make a prediction with MSSM. If you start adding a singlet to this and that, you wash out everything. So
I think this is one of the best examples of what we wanted for this conference, a benchmark of physics at 10 TeV that is really
it can be a benchmark. Not that you have to believe it, but at least it's the clear.
SUSY again.
Before a split, the motivation for split was grand unification and dark matter. And then it was introduced when the Higgs mass was still not known. So maybe it could have been 140. And then, of course, you need the scalars to be even higher. Nowadays, right, this is the picture. So you can still be at 10 to the 5. You can do anomaly mediation, for example. I didn't talk, right? In which, in that case, there will be a loop, a hierarchy between the scalars and the fermions. You could have a Wuino dark matter, maybe, or Xeno. So if you want to take seriously dark matter, then maybe you want to do. Yes. But yes and no. I mean, it's not super simple. I mean, once you dig in, everything it's because Wuino are, I don't know. Now there are some hints that maybe indirect detection disfavor them. And if you want to Xeno to be dark matter, then you need mu to be light, and then you can run again these arguments, and it's not that simple to arrange tangent beta to be smaller, sometimes mu to be ever successful electrochemistry. So there are some tensions. So it depends how much you want to take them seriously or not.
Okay, thanks again.
Yep.